Guys, this is a problem on packed bed reactors. It's going to be a two-part video. The reason why is there's a lot of information and some dimensional analysis involved with it. So I want to start this problem by first getting the total weight of the reactor, and then we'll work our way down using the material balances to develop an equation, and then in the second part of the video we'll come back and we'll solve it all the way through for the percentages, okay? So let's begin. So the first thing we got to do is we got to get the weight of the reactor, because if you read this problem carefully, I suggest you pause the video, but you end up getting, they give us density of the packing. So our density of the packing is equal to 0.99 grams per centimeter cubed. They give us a total surface area of the packing of 25 meters squared. And then they give us kind of like a density, but the surface area per unit volume. And that's kind of a conversion factor I'll show you how to use here in a minute. And just to make some more physical sense of what these mean, this means if you grabbed a little centimeters cubed, which is the same thing as a milliliter, if you grabbed a milliliter box and shoved the packing into it, it tells you that 150 centimeters squared of surface is available for the fluid passing through. That's how much contact it's going to make. Now this tells you the total surface area packed in to the entire packed bed reactor. So as the fluid flows through all these beads and goes this way, it's going to come into contact with 25 meters squared of packing surface area. And then this tells you for every centimeters cubed how much actual weight is in this box. So basically this 1 milliliter box, it's telling you it weighs 0.99 grams. Okay, so how do we get weight from that? Well, you can look at the units and quickly say, okay, you know what, I know where I'm going to kind of start. I always start with how much of something I've got. 25 meters squared. Now you can see all these guys are in terms of centimeters cubed, right? So what I want to do is convert that to centimeters cubed, and that's a relatively easily made calculation, and square it, right? And then what I want to do is, okay, now I got that in total surface area exposed in terms of centimeters. So I want to get in terms of volume to use my density, right? So I'll do 150 centimeters squared, 1 centimeter cubed. I use this guy. And then the next one, I want to now convert that to grams. 1 cm cubed equals 0.99 grams, right? So then that'll give me the weight of packing, big W, right? So big W, using this, don't forget this exponent when you make the calculation, but I did it in MATLAB already. It's 1,716, right? Grams. So that is what we needed from all that information, right? So now we can go ahead and do the material balance, accept the equation, and then I'll cut off the video and we'll go about, solving the rest of the problem. Okay, steady state conditions. I said that in the previous video. It makes that 0. Our FA in is FA naught. FA here plus RA dV. dV, on a quick reminder, is we're doing plug flow analysis, even if it's a packed bed. There's the same type of analysis, and we're going to go a differential weight down the reactor, meaning that if you pull this little plug out, this differential size plug, it's got an infinitesimally small weight. And we're using that because when we do our generation term, that we'll be dealing with this little differential. That's where our analysis is beginning. We're not going to put volume like we do in a lot of other stuff, or in a sense, total weight. We got to integrate down the reactor in this direction to develop the equations necessary. Okay, so FAO. Now for FA, we got to use the incremental step theorem, right? I discussed that in a previous video. So minus FAO, plug it in. Because of the negative sign, you're going to get negative FAO, negative here, because of this guy. And, yep, so negative DFA, DW, plus RA prime, DW, equals 0. Right? So you can see these two guys cancel, and then these divide to the other side. Now we can introduce conversion. I'm going to show you in a second how we do that. Equals 0, right? So we introduce conversion by saying, okay, well, let me separate these guys. FA is equal to FA naught 1 minus X. And the reason why this is the case is because you're dealing with a liquid. Otherwise, you'd have an expansion factor accompanying the flow rate and all stuff like that. So for now, okay, let's move DFA, DW, negative RA prime. Now let's put in our, one more thing. Do the derivative of this function above it, with respect to x. That's going to give you negative FAO. So then DFA is going to be equal to negative FAO dx. Yes. So then FAO is equal to dx dw negative RA prime, right? So now let's rearrange this whole equation so we can get W on one side. That would give you FAO dx over negative RA prime. Now, from here, I'm going to start the next video from here, just because I do not want to run out of time and I want to go nice and slow, because we're dealing with a second order reaction, and that can be kind of difficult on the integration, especially when most examples include first order. I want to go nice and slow so we can get it right. Alright guys, I'll see you guys in the next video. I can assure you this will probably be on the exam. So, alright, let's do it. Second part coming up soon.